Good morning. Hope you all had a wonderful Labor weekend. Before we move on, let me remind you that we do have our very first quiz, which you can practice. It is available. You can take it multiple times. You can check how it is. It is a practice quiz, though, because last week we collected homework assignment versus the quiz. Now this week, we're going to do the same on Friday. We're going to toss the coin, and then depending on what we get, you are going to get a practice quiz or a quiz which is going to be graded. But at least those of you, I see that some of you already tried it. Those of you who tried it, hopefully should get a sense of what type of questions we generally ask. And if you did it, you probably already have seen that it's kind of similar to what we did in homeworks and what we did in classes and what you did during the discussion section. We are also going to have your first discussion session, and I do have a couple of rules I want to reinforce. We really want you to work in groups, and the reason for it is because you see me solving things. Probably sometimes it looks quite easy, but then when you need to do it on your own, sometimes you get confused or not sure. Sometimes you make mistakes, even though you feel like you did it correctly. It's always helpful to have another set of eyes looking at the same questions you did. And then also you can discuss things and figure out where things went wrong or what is the best way to solve the same problem and so on. It is really for your benefit. Now, if from some reason you cannot really attend the discussion in person, things happen. Somebody gets sick sometimes there are appointments you have to attend. Again, life happens. First of all, I want to remind you that we are going to be dropping two lowest scores of the discussion. So if you didn't submit one of the discussions, it's not the end of the world. It's not going to affect your grade as long as you do well on the others. This type of an accommodations for all of you. But then the other option is join the Slack. We do have on the Slack a channel called discussion assignments. Just pause there, like look there. If you have to miss it, you can find people who also missed it and do it together with them. You can set a Zoom meeting, or you can just send each other solutions and discuss things. You can also discuss it on Icon. You can create your own discussion group similar way. So please, please, please do it in groups. It makes it's pretty much the best way to do those assignments, because I believe questions I'm trying to put out there do require some discussion sometimes. Okay, there are different ways sometimes to approach things and so on, and it's good to see what details you're missing. It is going to be especially important for today's discussion because it's going to have a lot of proofwriting, and everybody does proofwriting a little bit differently, and also because students tend to skip things or feel like this is obvious and not write them down, and then when somebody else reading it, it's not obvious at all, correct? So this is where you can point to each other, what are the steps which are missing, and so on, and together learn how to write a proofwriting. That makes sense? Yeah. Okay, great. On that note, do you have any questions? Okay, I don't see anything in chat, so let me share the screen. And let's go. Okay, so let's see. We are working on the direct proofs right now. And I have started by saying sometimes you can prove something by starting with a regional kind of like an if-else statement. Most of the proofs have a type of if some of the condition met, then something happens. The direct proof is going to start by assuming P. So you're always going to say either let M and N be integers and M and N are odd. So pretty much in this case, I have integers, two integers are even. This is my, this is my claim. If I have two even integers, then the sum of them must be odd. Okay, we are in section 1.7 and I see there is a question for 1.4, but I'll have to go back to it later. Okay, let's do some new material first. In this case, my P is I start with an idea. I have two even integers, and then what I have to do is I have to prove the sum is odd. You must use the definitions. So you always must to represent it in form of, in order to prove something is odd, you must end up with saying it's in a form of 2 multiply variable plus 1. If you didn't do that, you made a mistake. It must end up in something like this, 2 multiply variable. Do you see it? 2 multiply z. So it must end plus 1. It must end in the form of either 2 multiply variable for even or 2 multiply variable plus 1 for odd. Now, saying something like in a proof of something else, something like odd plus odd is even, is not going to be true. You cannot just say odd number and odd number is even. All type of those sentences will require a proof from you. You do not assume this knowledge. You must prove those little things as you go. Now, things you cannot do. You cannot start by saying, assume sum of two integers is even. Now let's prove one of the two integers is even. You can actually even see that it's not going to be true because sum of two even numbers is also even. So it's not always true. This is why it's important to understand what is the starting portion here and what is the ending portion here. So things not to do. No shortcuts. What I mean, don't say even plus even equal even. Obvious. It's not obvious. It requires proof. This is what I mean, this shortcut. This is where you skip things you shouldn't be skipping. To show me the sum of two even numbers is even, you will have to use 2x form. Now, another thing. Sometimes people write something like assume M and N are even. Then exist k integer such that M is equal to 2k, N is equal to 2k. I'm saying that that is a mistake. Who can tell me why it is a mistake? Okay. Here we go. I have a winner, Cody. Good job. Everything else is not correct. But k is a variable I picked. K is kind of, after you say it's a K, it's kind of like a peak number. It's like 4. It's set in stone. What I say here is not only M and N are even, but also I say this implies M equal N because they have an exact same representation. Do you see it? Although it's a variable, it's a fixed variable. After you fix it, that's it. You cannot assume M is equal to K and N is equal to 2K because this is more than what was given. What was given, M is even and N is even. So what is the correct way to do it? Correct way would be to say exist K1 and K2 evens. M is equal to 2K1, N is equal to 2K2. Do you understand the difference? Okay. So now let's check how else we can prove things. So the direct ones are always start with assume P. So direct proof of P implies Q. The structure is going to be assume P, show using valid arguments, Q is true. Okay. Now, another way is called proof by contraposition, or it has a couple of names, or contrapositive. I generally say proof by contrapositive. The textbook is using proof by contraposition. It is an exact same thing. It's like 2 different ways of saying an exact same thing. So if you want to prove P implies Q, first find not Q implies not P. This is why I prefer to call it contrapositive, because you find the contrapositive of this sentence, of the proposition, and then prove it. So instead of proving P implies Q, we will be proving not Q implies not P. Now, remember, you need to use rules. Lots of times your Q might be a combination of things like one thing and another thing, or one thing or another thing. When you negate it, what should you use? So if I have a sequence saying P implies Q and R, and I want to find contraposition, what do I do to Q and R? When I negate it, what do I use? Yes, I will be using the De Morgan rule. So we're going to be flipping to or and negate both sides. So don't like, one of the things is when you start writing a proofs, people forgetting to use all the other things we have studied. We started with propositions so that you have easier time generating correct proofs. So that means use everything we have studied. Remember to use your De Morgan's rules. Remember to use everything we did. And you know how to find contrapositive, correct? We did multiple exercises where you had to do contrapositive. So now let's do examples of actual proofs. So I did show you using the truth table that P implies Q has logically equivalent. It is logically equivalent to not Q implies not P. Remember, this is what we did last time. We had the table and we showed they have an exact same truth table. They imply one each other. So pretty much we showed they're logically equivalent. This is why such proof works. Okay. So what we want is exercise. If x plus y bigger or equal to, then x bigger or equal 1 or y bigger or equal 1. So first thing, I want to find contrapositive. The reason for it, and again, x, y are integers, yes. Actually, you know what? Let's do x and y are reals. It doesn't matter in this case. So let's do r and y are reals, okay? So if you're going to start with x plus y bigger than 2, you're going to say x is bigger or equal 2 plus y, correct? And there is not going to be much you can do with it. That's pretty much all you got. Agreed? But I want to prove it somehow. So how do I get to x bigger 1 and y bigger 1? Well, in a direct way, there are ways, but they're extremely complicated. So it's easier here to start with contrapositive. So we are going to be doing proof by contrapositive. In order to do it, I first need to find the contrapositive of current sequence. So who can help me? What is the contrapositive in this case? So this is my Q, and I need to negate it, correct? So I need to say if not Q. So how do I say not Q in this case? Correct. So if x is less than 1 and y is less than 1, then x plus y is less than 2. Lovely. So we have a new sequence, and now I can use it. So this is what we want to prove. So assume, this is the beginning of my actual proof. Assume x, y are real numbers and x is less than 1 and y is less than 1. Then x plus y is less than 1 plus y. I'm using here the fact that x is less than 1. So I can replace it with 1 and make the whole thing bigger. I can now also use y bigger than 1 and replace y with 1. And finally, 1 plus 1 is 2. So x plus y is less than 2. Proved. If you just write this thing to me, although it looks obvious, it's not obvious. It requires all of those explanations I just did. I know when you do things in like other math classes, algebra and so on, you can skip steps and everything, and you use those things, correct? Pretty easily without any explanation. But actually, for proof writing questions, you do need to use explanations. Since x is less than 1, I can replace x with 1 and make this whole expression bigger. I do not say it's now equal. I say it must be bigger. So when I replace x with 1, I say I make the whole expression x plus y larger. So x plus y has to be less than 1 plus y due to the fact that x itself was less than 1. Okay. The reason to replace both of them with 1 is because I'm trying to get to x plus y less than 2. So I'm trying to show you that. If I'm just going to leave it as x plus y, it's not going to give me anything. I need to show somehow that x plus y is less than 2. And in order to do it, I can use things which are given to me. In this case, what's given to me is x is less than 1 and y is less than 1. And I'm using it one step at a time. I'm saying that since x plus y has x in it and x is less than y, by replacing x with 1, I make the expression larger. That's mathematical property. If you replace something with a larger value, you make the whole expression larger. So it's similar as saying 10 is less than 12, correct? So I can replace 10 with 12, but I have to specify that now I made this whole thing less, like bigger, correct? 10 less than 12. I can do it, correct? I can do 10 less than 13 and so on. In this case, I know x less than 1, so I can replace x with 1 and make the whole thing bigger. Okay, now let me check. I do not see the whole comment here. You have the expression 1 plus 1 is less than 2. Yes, it should be equal, less than equal. I'm missing my equal sign. So what I have here is this one is less than due to this part 2. Do we need then x over? Now, what I do here, if that's the question, is I specify what exactly I use to go from one space to another. Okay? The reason for it, even though it looks like pretty simple, when you read somebody else's proof, you do not know what they thought of, correct? And sometimes it's hard to see what rule was used. So I generally specify, I explain in words what exactly I did. Now, Rabbi, the contrapositive is strictly less than, correct? There is no less than or equal, and it is strictly less due to that. The fact that I later found something which is equal, that's fine. I do have this portion strictly less than due to the very first one. And I cannot use equal in here. So I can ignore this equal because I do not have it here. The rule is I had strict less than. So later x plus y actually strictly less than 2. Now, 1 plus 1 is actually equal to 2, and that's fine. I only need one of those in the sequence to make it winning one. Okay. In that box, is it less than or equal to? It's less than because that's what we assume. There is no equality here. And there is no equality here because when I replace it with 1, I make the whole expression larger, strictly larger, due to x is strictly larger than 1. Okay, so let me get rid of this so that you can see it nicely. So this is what I have. Yes, we will do more examples of different types of proofs. So let me continue and do more and more because they are going to become more and more complicated. They're going to have inside those little portions. So we will do it many, many times. Okay. Okay. Another one. Definition. A number is rational if exists a number n is rational if exist pq integers such that n is equal to p divided by q. Prove that difference between two non-equal rational numbers is rational. So in this case, I want the difference between two non-equal rational numbers is rational. So what do I start as? I want to prove the difference is rational. So what do I start with? Two different rational numbers. Okay. Let n and m be two non-equal rational numbers, then exist P1, P2, Q1, Q2, all integers such that n is equal to P1 over Q1 and m. This one is a direct proof. And then m is going to be equal to P2 over Q2. Now let's look at the difference. So what is n minus m? I really want to bring it to the form integer divided by integer. So I want to bring it to the form of x over y or k over t or whatever letters you use. How can I do it? Well, in this case, we're going to first replace m and n by the things we did. And now what should I do? I want it to have in the form of fraction. So how do I make it a fraction? What do I need to do? Right now it's fraction minus fraction. How do I create one common? Yes, common, it's called not common factors, but yes, Evan, common denominator. Good, cross multiply, Trevor. Yes, that's correct. That's the rule of remembering how to do it. So what we're going to have is we're going to find the common denominator and we're going to have z. Now, remember, if I have two integer numbers and I multiply them together, I do get another integer. So what I can say is I can say that this is x over y, where x, y are both integers. X is equal to P1 Q2 minus P2 Q1, and y is equal to Q1 multiply Q2. And we are done. We proved it. So okay. Let's talk about another way of proving. It's called proof by contradiction. The non-equal part in here is important because otherwise the difference is just 0, and 0 is depending on how you argue, it is either rational or irrational because it's 0 divided by y, so it's kind of rational, but it's better to avoid it. And yes, I can go back. Multiple of two integers is integer is actually does not require a proof because when you have two integers, it's a property of integers that integer multiply integer is actually an integer. There is no way to prove it because then how would you prove it? 1 plus 1 is integer, 1 plus 2 is integer. I'm going to list every possible integer combination for me. So generally we assume that if you have two integers, the addition of them, the subtraction of them, multiplication of them is an integer. However, you cannot really specify that integer divided by integer is integer because that's not always true. 5 divided by 2 is actually going to give you real number, correct? 2.5. So you can use it for addition and multiplication and subtraction, but you cannot use it for the division. And you only can do it as like, you can also assume real multiply real is real and so on. Those are just properties of integer numbers. Okay, so prove by contradiction. Okay, so proof by contradiction is you are going to assume not P. So you want to prove P implies Q pretty much. And what you are going to do is you're going to say if you're going to prove not Q implies Q, oops, sorry, not P, implies Q, Q is false. So the best way to see it is using an examples. It doesn't always have to be in that form. Sometimes it's more of you just use not P. So assume you want to prove P. What you really want to do is to prove P, show not P is always false. That's kind of a thinking behind it. But for P implies Q, you can assume not P and show contradiction. So There are like different ways of playing with it. But generally what you do is you're trying to say if whatever you're trying to prove is not true. Here is an example. Okay. So this is a type of where I do not have if else, correct? I just want to show you that square root of 2 is irrational. Do you agree that square root of 2 is irrational? I'm sure you all know it. The question is, why? How do you know? Maybe there is a fraction. Maybe maybe you just didn't find it. Well, actually, I can prove it to you. And here is how we're going to do. So I'm going to assume by contradiction that square root of 2 is rational. Then exists PQ integers such that square root of 2 is equal to P over Q, and P over Q is simplified form. Oops. So who can remind me what is simplified form? What does it mean for a fraction to be in simplified form? Yes, I cannot really factor it. That means there is no way for me to factor it. They do not share. So pretty much P and Q do not share common divisors. Okay, so square root of 2 is equal to P over Q. I'm going to take both sides into the power of 2. Okay, then we are going to have 2 equal to P squared over Q squared. That means, so implies that P squared is equal to 2Q squared. Claim. P is even. Okay, so B1, at some point of time, you asked me about like differences between lemmas and theorems and so on. So this claim I'm going to call lemma. My lemma is going to be P squared equal to 2Q squared implies P is even. And I'll have to prove this lemma for you. Okay? So we're going to leave this piece for now, and we're going to trust that's true, and we're going to keep on working. And then on a separate page, we're going to do this one separately. So this is a small portion which I need for my proof. Does that make sense? So this is like why it's a lemma. It's a small thing, small claim. But it requires proof, so I still need to prove it. So remember, I own you this piece. But now, if P is even, then exist k integer z such that p is equal to 2k. Now let's go back to here. So we have p squared equal to 2q squared. And now I'm going to substitute. So I'm going to have 2k squared equal to 2q squared. I substitute instead of p 2k. Don't forget parentheses because my square is going to be for both 2 and the k. Next, it's going to be 4k squared equal to 2q squared. Divide both sides by 2. I'm going to get q squared is equal to k squared. But look at my lemma. Look at my lemma. Do you see my lemma? So what can you tell me about my q if my lemma is true? Q is even. Wait. Contradiction. P is even. Q is even. But what did I assume? Simplified form. Good. Yes, correct, William. Now, contradiction generally is drawn by this like lightning. I call it lightning line. So it kind of say it's impossible. So by contradiction, I proved that square root of 2 cannot be rational, correct? So I started with saying it's rational and I showed you it's impossible. Well, I kind of showed you, but I also kind of didn't because we have this strange lemma, correct? Okay. So let's look at what I had. I had p squared equal to 2q squared, and I said p even. Okay, this is what I had. This what was my lemma. But now let's see. I have 2 here, correct? So pretty much what I really have here is p squared is even implies p even, correct? Agreed? This is what I have here. So here is my lemma, the one I plan on proving you. If n squared is even, then n is even. That's what I want to prove for you. And this is for those who asked for another contrapositive proof. So in this case, if I start with n squared being even, I'm going to have n squared equal to 2k. And I will be sitting there and thinking, what do I do? Should I square? Square root is not my friend, correct? We do not like square roots. I do not want square root both sides. So I need to find something better. You always prefer to start with something simple like n is odd or n is even or n is rational. You do not want n squared to be something. So we are going to prove it by contrapositive. So the contrapositive, this is my P implies Q. So now the contrapositive statement is going to be if n is odd, then n squared is odd. Do you agree that this is my contrapositive? And now let's do my proof. Assume, and again, remember, n is integer. Assume n is odd, exist k integers such that n is equal to 2k plus 1. N squared is going to be 2k plus 1 squared, which is not equal to 4k squared plus 1. So you need to distribute, correct? So which is going to be 4k squared plus 4k plus 1. Do we agree? FOIL, which is the same as 2 multiply 2k squared plus 2k plus 1, which is of a form 2i plus 1. I is integer because I is 2k squared plus 2k. So n squared is odd, and we are done. So I proved your lemma, and I used it to prove a larger claim, which was square root of 2 is integer. Okay, next. Prove by counterexample. To disprove a statement, it is enough to provide one example. So sometimes you see a statement and it says prove or disprove. And if you feel like this claim is not correct, in order to prove it, what you really need to do is you need to give counterexample, an example which is going to show me that's not true. It's not happening. One example is good. Now, remember, it's only good to disprove statement. You really cannot use it to actually prove anything. You kind of only can prove it wrong. You only can prove wrong things using example. You cannot prove right things using example. Now, so one of the examples is going to be, okay, easy. My statement is going to be all the students in my class are boys. And then I'm going to pick one of the boys in my class. I definitely have some, right? Am I right? Is my claim correct? No, correct, because we have all type of genders in our class. So picking one example, one person in the class and saying now everybody is like this is not correct, right? However, you can say, okay, your claim is false. And how can you prove me that my claim is false? You can just give me one example of a girl in this class or somebody else. Does it make sense? So this is why you cannot say it. And again, it can be like, all integers are even. And you can tell me, no, 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 wait for it. 3 is not even, correct? So pretty much it's a real life thing. You cannot just say it works for that one, so now it's true for everybody. In order to prove it for everybody, you need to do it generally. This is like an arbitrarily. This is like a universal gosh, I have generalization. So don't do it. This is the one which you shouldn't do. You shouldn't say it's true for one, so it's true for all. That you cannot do. But you can say it's not true for one, so it's not true for some. Okay, so the statement is incorrect. So here is an example. Where is it? Sum of two odd numbers is odd. You can say no. 2 plus 2 is equal 4. Even. So you proved by example. We are done for today, and I'll see you on Wednesday.